Good morning, good afternoon, wherever you may be in your day. Thank you, as always, for choosing to make general chemistry part of your day. Couple bookkeeping things up front. This video is actually going to end the material in test number 4. Trying to give you a clean break around Thanksgiving break so we can start fresh when we come back and we don't have to bridge that. We're going to have a quick turnaround, quick test beforehand. So I'm actually really optimistic the grades are going to be good on this test, so take advantage of it. This will end the material for pre-Thanksgiving, and then post-Thanksgiving we'll have new material and we'll go from there. Okay, so objectives, you can read them, pause it, take a look at it, but we're going to look at a couple things. Quickly, let me review. Hope you liked the periodic trends video. From a historical standpoint, that was the first YouTube video I ever made, so I want to just discuss real quick what we made of that, and hopefully that seems smoother now, All right, so size and radius is going to go kind of opposite of everything else. It's going to increase this way and increase this way. Remember, francium. France is a large country in Europe. It's a big element on the periodic table. And then this side's small, that side's big. Boom. Then we talked about electronegativity, the ability to hold electrons within a bond, the ability to resist an electron being removed, ionization energy. And I want to add one more thing here, the ability to add an electron called electron affinity. And we'll talk more about this as we go on the board. But what I'd like to point out is, really all of these things are the same, right? It's the atom's ability to hold on to electrons. If it's good at holding on to electrons, they're tight and they're small, which means it's good at holding on to in a bond itself, not letting it go away, or taking on more. Likewise, if something is big and its electrons are wandering about and I don't even know where my kids are, those darn teenage electrons, I don't know where they are. The electrons are held very loosely in a bond. They're held loosely in the atom. It's easy to remove one, and it's hard to add more. So that's our trends, and the two real things I want to do in this video is talk about what happens if we change the charge, and what happens if we go on more than one electron change. Well, we do 2, 3, 4, 5. Oh no! So let's talk about charge. And I'm going to do this as simple as possible. I'm not even going to belabor the point. I'm going to do it the common sense way. I won't even get into the repulsion and the electrons and all that other nonsense. If you add electrons, so electron affinity, if we add electrons, you make negative charges. Negatives do not hold negatives well. Ionization energy therefore goes down. The ability to hold electrons, electronegativity in a bond goes down. The ability to add more electrons, electron affinity goes down. They get further away, size goes up. If you do want the scientific explanation, there's more electrons to repel each other, pushing them further away from the nucleus is called more shielding. Okay, but I told you I wasn't going to do that, so I didn't do it. All right, now if we go the other way, we make cations, ionization energy, things with a positive charge. Positives hold negatives. Awesome! They hold them tighter. It's harder to remove them. Hold them tighter in a bond. They can take even more electrons in. Give me an electron. Sure, I love them. And I love them so much, I held them in tight. My size is smaller. Again, don't tell Dr. Wargo, but the science behind this is the nucleus is the same size. There's less electrons to hold in place and less shielding and repulsion. Okay, we got it. All right, so what would that look like in a multiple choice problem? That's a good question you ask. As you can see, you're focused on the test. Not the greatest idea, focus on knowledge, but we want to apply, so I'm with you. All right, rank the following from smallest to largest radius. So, they're all the same element. They could all be the same. They're not. So we're just looking at charge. So remember, I'm going to put carbon in the middle. Does adding electrons make it bigger? Let's use common sense. We add to something, does it get bigger? Absolutely. So if we take away things, it gets smaller, and if we take away more things, it gets smaller still. So you would just rank by charge, going from the most positive as the smallest to the most negative as the largest. What if we were to mix elements? Well, there's two pieces here. First of all, the positive charges are going to be smaller. So I know these are my two smallest, and I know the neutral atoms are my larger. But the question is, how do they rank compared to each other? And then I have to go to my old friend, the periodic table, and find those two guys. Or gals, if you prefer. So I find these gender-neutral atoms hanging out right here on the far left of the periodic table. But what we notice is calcium is underneath magnesium. So remember, going back to the trend in the board I just slid away, bigger things on the bottom. So calcium is larger than magnesium, which means calcium cation is also larger than magnesium cation. So you would you'd differentiate by charge, you'd sort by charge. So we know these two are the smallest. And we know, likewise, these two are the large, because they're the same charge, or the most negative charge in this case. And then within, so we sort by charge first. Then go to the periodic table and find position. So, just to reiterate that all of these things are asking the exact same question, just in a different way. What if I change the question to which of the following would have the largest electronegativity? So again, the largest electronegativity is going to be the smallest size. So this would be magnesium 2+. It's the smallest because it's holding onto its electrons the tightest. What would have the largest ionization energy? Again, everything runs opposite of size, so if we want the largest, we really want the smallest ion, and this again is magnesium. And which would release the most energy when gaining an electron? Well, this gets into a definition that I haven't quite defined very well, which is on the next slide. But gaining an electron, again, which one's going to be the best at gaining an electron? Well, it's going to be the smallest one, the most positive one. So again, that's magnesium. So different ways. And of course, I could change this to smallest, least, smallest. And then, of course, the answer would be the calcium, calcium, calcium. So again, read carefully, think about what they mean. And those are, that's pretty standard test questions I would ask. All right. So the promised definition. Electron affinity is the amount of energy associated with gaining one electron in the gas phase for one atom. So there's a lot of ones here that are implied. 1, 1, 1. So we're taking one gas phase atom, one electron, and forming whatever we form. So if we take the first electron affinity of oxygen, it would be oxygen plus an electron forms oxygen anion. This is going to be mildly exothermic or have a negative value. You could write delta HEA if you wanted to make it look like an enthalpy change, but either way, it's an energy change. Now what's interesting is we look at the second electron affinity. So now we're going to get into the specifics of the definition. It's always adding one electron. So the second electron affinity is going to be adding one electron to create the second charge. So if we look at what's missing, the second electron affinity of oxygen, it's going to be oxygen where it's already lost one electron, then gained one electron, then the second one comes on, and we form the -2 charge. So the number of the electron affinity is the charge we form, and we always, by definition, add one electron, and we also, by definition, have it in the gas phase. This is to minimize other interactions. The gas phase, the particles act by themselves, and we don't have to worry about geometry, bonds, other nuclei being around, so we can actually isolate the energy we're talking about. It'd be much harder to do the same experiment or talk about this if you had anything other than that in the gas phase. So, okay. So what's going on here? And this one is moderately endothermic. So this might be like -50. This might be +300. That's a pretty big difference in energy, kilojoules. What's going on here? Well, here we're adding an electron, so you could think of this as like forming a bond. That's going to be exothermic, right? We'd still get a little bit of exothermic event here from the electron adding to the oxygen, but the problem is we have to put in a bunch of energy to overcome the negative charge repulsion to get them close enough to form that bond. So the energy it takes to overcome that repulsion makes this an endothermic process. And generically, this would be your generic reaction. Always one electron to form whatever the charge is that you're told. So if it's the first, it's -1. Second, -2. Third, -3. And really, you don't go past that. Actually, you really rarely see anything past -2. Ionization energy works the same way. But before I get into the series of ionization energies, I want to talk about the exceptions to the rule. So if we were just to take a chunk of the ionization trend and look at our atoms moving left to right on the periodic table and look at ionization energy, certainly the general trend is going up. But what we notice is boron and oxygen appear to have too small an ionization energy. So why? Well, of course, if we want to know why, we got to start thinking about what's really going on. Here's boron, here's oxygen. Undergo the first ionization energy and remove an electron. When we remove that electron, we leave behind a state that is full and empty. And if we look at oxygen, we leave behind a state that is full, half full. And again, these are equal electron distribution clouds. This gives stability. Again, a noble gas is not noble because it has 8. Matter of fact, most of the noble gases don't have 8. They have 2. They have 18. They're stable because you've equaled out the electron cloud. You've pushed all the negatives equally apart from each other. They're stable. So again, these are more stable states. You're seeing this reflected in slightly decreased values of ionization energy. If you were to take a professional chemistry exam, this is kind of standardized testing question you might see. Let's talk about series of ionization energy. So we remove the first electron. We leave behind something with a positive charge. Remove the second electron. Woo, positive 2. It's getting harder to remove these electrons. Remove the third one. I got to pull it off with positive 3. Pull off the fourth. We leave a positive 4. So the charge is getting bigger and bigger and bigger. It's getting harder to pull these electrons off. Generally, so this is always true. First ionization energy is always smaller than the second, always smaller than the third, always smaller than the fourth, yada, 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 until you run out of electrons. General rule of thumb for valence electrons has to be valence. First ionization energy is about 1,000 kilojoules. Second ionization energy, about 2,000 kilojoules. Third ionization energy, about 3,000. You get the trend. It's not so hard. Just add 1,000 after the number. If it jumps greatly or deviates greatly from this trend line, you're no longer talking about a valence electron, you're looking at a core electron. You're going to see the number go way up. If the number is too small, it's okay. But if that number is way bigger than 4,000 for the fourth, you're talking about removing core electrons. So how is this useful? Well, the amount that follows this general trend equals the number of valence electrons. So I've given you real data here. 787, 1577, 3231, etc., etc., etc. So, is that roughly 1,000 or less? Yes. Is that roughly 2,000 or less? Yes. Is that roughly 3,000 or less? Sure. Is that roughly 4,000 or less? Sure. Is that roughly 5,000 or less? No way, 16,000. That's way different than 5. Okay. Good. So that means this is a core electron. And everything before it was valence. So if I look, I see 1, 2, 3, 4 numbers that follow the trend, and I would know that this particular atom had 4 valence electrons. And I could go to the periodic table, and if I said this was, say, a third period element, you would just count across 4 blocks in, and you might see something like silicon. Or I can make this multiple choice, and I could give you aluminum, silicon, whatever else would be in that area of the periodic table. And you'd pick the one that's 4 blocks into the periodic table. Anything 4 blocks in could have a trend that looked like this. So you're just looking for the big jump. When you see the big jump, count how many numbers you had before that, and that's your valence electrons. Count that many blocks in the periodic table, and you are in the right spot on the periodic table. That's really all I have on this. I probably should have written a generic, same idea with ionization energy. It's just going to be a metal in the gas phase goes to an electron plus the metal with the charge given. It's always 1 electron at a time, and this would be n-1 for the charge. So if I had this fourth ionization energy for silicon, it would be silicon 3 plus in the gas phase goes to an electron plus silicon in the 4 plus. So this would be I4 for silicon. So the 4 becomes the charge, the element's the element. It's always gas phase, and it's always 1 electron. So write the back part and then add it up to get to the left. And that wraps up our material. I hope you're having a fantabulous day. And good luck on the large chance to demonstrate your chemical knowledge. Safe travels if you go anywhere for Thanksgiving. And I hope you enjoy the break. And I hope you come back refreshed. And we will talk about Lewis dot structures and geometry, or what the acorn said when it grew up.